All right, section 3.4. So this is all about absolute maximums and minimums. So in the last couple sections, we've been discussing local maxes and local minimums. So we have two things to talk about here. The first is, of course, actually both things are about absolute extrema. So remember, extrema just refers to our maxes and our mins simultaneously. So absolute maxes and mins. And this is with what I'm going to call principle 1. And then we have the same thing, absolute extrema, with principle 2. So essentially what we're going to be doing is building two ways to talk about our extrema, our absolute extrema. And we'll discuss each of them in detail. So the first, we just need to define our extrema on a closed interval. So if f is a defined function on some interval I and it's containing the value c, first off, f of c is an absolute extrema. And we're actually going to go one step further, absolute max. If f of c, not enough space there, f of c is greater than or equal to f of a for all x equals a in that interval I. So essentially, we're bigger than everything on that. Now, there's no difference between this definition and what we saw in previous sections. The difference is our interval is closed. So for local extrema, local maxes, local mins, we were looking at open intervals. Now we're looking at closed intervals. So keep that in mind as we move through. And then similarly, f of c is an absolute minimum if f of c is less than or equal to f of a for all x equals a in our interval I. Again, no difference between our definition for local minimum, except our interval I is closed, just like for the one above for absolute min. So the absolute min, the absolute max of a function on a closed interval are what we call the extreme values, or absolute extrema, as our section is titled. And it's always a closed interval. So when you have an open interval, you can still have absolute extrema, but we typically look at closed intervals for extreme values. So before we dive into finding extreme values, I have two graphs here. And what we want to look at here is considering a continuous function. So our domain is a closed interval, and we have two graphs here. The absolute maxima and the absolute minima occur for each interval. So since we're closed, we only have to worry about from here to here. And the way that we handle this is we look at the start of our interval at A, the end of our interval at B, and then just as we did in the previous sections, we find our critical numbers, C1, C2 in this case, and we compare all of them to this definition. So the thing that's biggest, the y value that's biggest, is this. So this right here is the absolute max. And the thing that's smallest is this one right here. So this is the absolute minimum. Now if you're wondering, well, what's the difference between what we did in the last sections? Well, in the last sections, we would ignore the endpoints. And we'd say, well, don't look at these, just look at the critical numbers. Well, if you look at your critical numbers only, you'll miss your absolute min because it's part of your interval. It's the endpoint. So we have to account for the endpoints. Same thing over here on this function. we look at the start and the end at the a and the b of our interval, and then we find our critical values. Once again, for this example, there's just these two. The largest thing is the absolute max, and the smallest thing is the absolute min. So in this case, both of our critical values form our absolute extrema, the max and the min, respectively. So it's important, that we look at our critical values first, and then we check our endpoints to make sure we don't miss anything. So that leads us to what we call the extreme value theorem. That's what this box is for. And the extreme value theorem says if f of x is continuous on a closed interval a to b, then f of x attains its absolute extrema on a to b, on that closed interval. Now this may seem like an innocuous theorem, but it's actually very important, because what this is saying is that we know continuous functions, or just functions that are continuous on closed intervals, will always have an absolute max and an absolute minimum. Excuse me. So we can go back to these examples. These are continuous, and so either the absolute minimum occurs at one of its endpoints, like it did in this one, or at one of its critical values. But it will always attain that value. Same thing with the absolute maximum. Now in both cases, these were at the critical numbers, C1 and C2 for these things here. But it doesn't necessarily need to occur there. It could also occur at the interval endpoints. Now there's something extremely important to keep in mind here, and that is that this theorem does not tell us where the extrema are. To actually find the extrema, we need to do some more work. But if we can find a continuous function, or find a closed interval that a function is continuous on, we know we hit those absolute maxes and absolute mins. We have to. So to actually find those minimums, we have the following. So the first is the maximum minimum principal one. So to find the absolute extrema of a continuous function f on a closed interval a to b, we use the following steps. So the first step, it's find the derivative. F prime of x is computed. So take your derivative. Second, find the critical points of f of x. Remember, that means f prime of x equals 0. Then, once you have your critical points, and remember, we're talking points, so this is the ordered pairs, the x comma y's. Once you have your critical points, we evaluate f of a and f of b. So now you'll have y values for all your critical numbers. You'll have y values for your ends of your intervals. Excuse me. And so the last thing is the largest y value that you found is the absolute max. And the smallest y value is the absolute min. So both of these are coming from either f of a, f of b, or the critical points you found up here. So let's try this out. We have the next example here. So find the absolute maximum and minimum value of this function over our closed interval, -2 to 3/2. So this is -2 3/2, not 3/3. Can't read that at all. Let's try that again. -2. Did it again, 3/2. Okay. So first step, find the derivative. F prime of x of, this is x cubed minus 3x plus 2. F prime of x will be 3x squared minus 3. Set this equal to 0. We have x squared equals 1, or x equals plus or minus 1. So I'm going to find f of 1. I'm going to find f of -1. And then in step C, we're going to find f of -2 and f of 3/2. So f of 1, just plugging into our original function, this is going to be 0. F of -1 is going to be 4. Again, I'm just getting these by plugging in here. F of -2 is going to be 0. And f of 3/2 is 7/8. So now that we have these, we take the biggest, which is this one. So that means that -1, 4 is the absolute maximum. And then we take the smallest, and now there's a tie for the smallest. And so when you have a tie, you do list them both. So 1, 0 and -2, 0 are both absolute mins. And those are our answers. So we take our derivative, we find our critical values, we get our critical points, getting the y values, and then we check our endpoints. Pick the biggest, that's your absolute max. Your smallest, or what's tied for the smallest, is your absolute mins. So let's try it again. Now this is the exact same function, but I've changed the interval here. So now we're going from -3 to -3/2. So we're going to change what happens. So our derivative, still 3x squared minus 3, still setting this equal to 0. That's still going to get us x equals plus or minus 1, because it's the exact same function as we had up here. So we're still going to have f of 1 and f of -1. F of 1 is still going to be 0, f of -1 is still going to be 4. So now all we need to do is check the new values. F of -3. So again, we're plugging this into the original, which is still x cubed minus 3x plus 2. So this is -27 plus 9 plus 2, and that equals -16. And then f of -3/2 be -27 over 8 plus 9 over 2 plus 2, and this is going to be 25 over 8. So now we pick the biggest and the smallest. So since we have a negative here, this is certainly going to be the smallest. So -3, -16 is our absolute min on this interval. And the only question now is 25 over 8 bigger than 4. 8 goes into 25, 3 times, not 4 times. So this is going to be our absolute minimum, or absolute, this is not going to be our absolute maximum. I'm losing my train of thought. Because 25 over 8 is 3 point something. So our absolute maximum stays negative 1 comma 4. So this is how principle 1 works. You find your critical values, you plug in your critical values, you plug in your endpoints. You pick the biggest and you pick the smallest. And if you have ties, you list them all. So let's turn the page now and take a look at how we handle principle 2, because we have a different way of doing things. So just like we had first derivative test and second derivative test, a little bit of a formatting error there. Then, so the setup here is we have a function f prime of x exists for all x in some interval I, and there's exactly one critical value. And this is the important part. There's only one critical number in your interval, and that means that f prime of c equals 0. Then f of c is the absolute maximum if f double prime of c is less than 0, or f of c is the absolute minimum if f double prime of c is greater than 0. And if you happen to get equals 0, which is what we're talking about in this passage here, so principle 2 holds no matter what the interval I is, whether open, closed, or infinite, if f double prime of c equals 0, either we use principle 1 again, or we need to know more about the behavior of the function over the given interval. So this is kind of like an analog to the second derivative test. If we only have one critical number, we can use it. If the test is inconclusive, we have to go back to principle 1, just like with second derivative test. If second derivative test was inconclusive, we went back to first derivative test. So let's take a look at how we would use this in the next couple examples. So here it says find the absolute maximum and minimum values of f of x equals 4x minus x squared. 4x minus x squared. So notice it doesn't give us an interval. When it doesn't give us an interval, the implication is that it's negative infinity to infinity. You're looking at the entire domain. So first step, we need f prime of x. We need our critical numbers. So f prime of x will be 4 minus 2x. Set that equal to 0. 2x is 4, so x is 2. So this is our c value. Notice we got 1. There's only 1 in this entire thing. So this is kind of our hint. There's only one critical number. So we want to use principle 2. So we look at f double prime of x. F double prime of x is negative 2. F double prime of 2, well, that's still negative 2, so that's less than 0. That means that negative 2, comma, we should probably plug that in, f of negative 2. What's that? Negative 8 minus 4. Oh, not negative 2, positive 2. I was looking at myself like I'm crazy. That's 8 minus 4, which is 4. So 2 comma 4 based on principle 2, our second derivative is less than 0, so this is an absolute maximum. Absolute max. So, in our next example, just like we did with principle 1, it's the same function. It's still 4x minus x squared. And our intervals change, though, from 1 to 4. Now we know our derivative, f prime of x, still 4 minus 2x. That's still going to give us critical numbers of, or critical number of 1. Now here's the difference. When we have 1, we use f double prime of 2. F double prime of x is still negative 2. So that means f double prime of 2 is still negative 2 is still less than 0. That still tells us this is the absolute max. But I'm going to put a question mark here. Because now that we have a closed interval, anytime you have a closed interval, we have to check the endpoints. So anytime you have a closed interval, must check the endpoints. Now for this particular function, based on our example up here, we know that this is the only critical number, and the second derivative is negative, which means it's going to be concave down all the time. So this should be the absolute max. What we're doing here is essentially double checking. So we know that 2, 4 is the absolute max in question. So we need to check f of 1, and we need to check f of 4. And based on what we did up here, we should get that these are both smaller than f of 2. So f of 1 is 4 minus 1, which is 3. Sure, still less than 4. F of 4 is 16 minus 16, which is definitely less than 4. So this is still our answer. But the big thing is, in this example to highlight, is you have to check those endpoints because it could change. This function doesn't, but that doesn't mean every function is going to work this way. So I have some strategies on the next page here and some practice. This is some strategies for finding maximum and minimum values, specifically absolute maximum and minimum values of a continuous function over any interval. Okay? We're not limiting ourselves. So number 1, every single time, find the derivative. Find f prime of x and find the critical values. Every single problem, whether you're doing local or absolute, you should be doing this if you're finding extrema. Number 2, this is where the strategy really comes in. If the interval is open, use principle 2. Right, 2 for 2. And the reason is our principle 1 doesn't handle open intervals. It only handles closed intervals. So number 3, if the interval is closed, check. Number 4, if there are more than one critical number, critical value, use principle 1. Because principle 2 doesn't handle multiple criticals. And number 5, if there's only one critical number or critical value, use principle 2. So every problem is going to start the same, though. You're going to be finding your derivative, and you're going to be finding your critical values or critical numbers. And then you're going to be looking at your interval to see what you should do. So in the case of finding absolute maxes and mins, when more than one critical value occurs in an open interval, such as those listed in step 5, it's dealt with by a detailed graph or by techniques beyond what we do in this class. So if for some reason you have an open interval and you're not looking at the end behavior, because that would be detailed graph. That's what we did in 3.3, was detailed graphs. You look at your end behavior, that helps you. Or if it's too complicated or there's too many, then you need something out that we just don't do in this class. So keep that in mind. So 2 practice problems here. I recommend you pause and try this out on your own. So for this first one, I'm going to give you an interval, -1 to 4, for this function. So pause the video and try this out. Follow your strategy here. See if you can find the right absolute maximum and absolute minimums. So I'm going to walk through it now. So first step, always the same. F prime of x. This is going to be a chain rule. So this is 3 times x minus 3 quantity squared plus 0. Set this equal to 0. And this is going to give us x minus 3 squared equals 0, or x equals 3. So we have one critical value. We're on a closed interval. So we're into step 3 of our strategy. It's closed, so now we check. There's not more than one. There's only one, so we're going to use principle 2. So I'm going to find the second derivative. Again, it's going to be a chain rule. It's going to be 6 times x minus 3 times 1. We're going to plug in our number, f double prime of x, or f double prime of 3 equals 6 times 3 minus 3. This equals 0. Well, remember, in principle 2, if we get 0, we need to use principle 1. So we need to calculate f of 1, or f of -1, f of 4, and f of 3, which I'll do over here in a second. So f of -1, -1 minus 3 cubed plus 1, this is going to equal -63. F of 4 is going to be 4 minus 3 cubed plus 1. This is going to equal 2. And then f of 3 is 3 minus 3 cubed plus 1. This is just going to equal 1. So we take the biggest y value, 4,2. This is the absolute max. And we take the smallest y value, which is -63. -1, -63. This is the absolute min. That's a 4. So this kind of goes through, this is a good example of all the steps, identifying what principle to use, And then if you come to an issue where the principle doesn't work, principle 1 always works. You move on to principle 1, check your 3 values because we only have 1. Remember, you should always be checking your endpoints if you have a closed interval. Biggest one becomes your absolute max, smallest one becomes your absolute min. We have our answer. So in this one now, again, I recommend you try this out on your own. So I'm going to walk through it now. You should have already finished your problem. So f prime of x. If I rewrite this as 5x plus 35 x to the negative 1, I know that my derivative is then 5 minus 35 x to the negative 2. And we set this equal to 0. So this is when 5 equals 35 x to the negative 2. Or when x squared equals 7. So x is going to equal plus or minus square root of 7. Excuse me. So now we're looking at critical numbers, and make sure you identify your interval. So because the interval is 0 to infinity, we're only going to be looking at positive square root of 7, since negative square root of 7 is not in 0 to infinity. So make sure you're accounting for your interval properly. So now we have one critical value. We have an open interval, which means we need principle 2. So f double prime of x is going to be positive 70 x to the negative 3. F double prime of square root of 7 equals 70 over square root of 7 cubed. Now I don't actually need to know what this value is. I just need to know that when I cube the square root of 7, it's going to stay positive. So this is positive. And so the square root of 7 means that we need to calculate the square root of 7. So this is 5 rad 7 plus 35 over rad 7, which equals 5 rad 7 plus 5 rad 7. This is 10 rad 7. So I got from here to here just by rationalizing, times by square root of 7 times by square root of 7. This becomes 35 over 7, which is 5. So square root of 7 comma 10 square roots of 7, based on our second derivative, is the absolute min, because it's positive, so it means it's concave up. And if you were to look at its end behavior, so think about graphing this, you would take the limit as x goes to infinity. This term goes to 0, but this term, this 5x, goes off to infinity, which means that it has no absolute max, which checks out because we shouldn't have any absolute maximum based on our work here. So because I don't have a lot of space left, but make a little room here. So since the limit as x goes to infinity of f of x equals infinity, there's no absolute max. Now some of you might be saying, well, what about if we go to negative infinity? Well, you'd be right. If we go to negative infinity, this goes to negative infinity, which means we shouldn't have an absolute minimum. Now that's on the whole domain though, because our interval that we're checking is just this 0 to infinity. So going towards negative infinity doesn't make any sense. So a lot of times you'll see this, a restriction placed on the domain to ensure that there is an absolute extrema. If you take away this restriction and you just have all real numbers except 0, then you would have no absolute max and no absolute min. And that's what's happening here. Okay. So that's the end of 3.4, absolute extrema.